Despite the mystery and the importance of the Higgs particle to the Standard Model, my favorite is still the neutrino. Far and away, it's the most intriguing and appealing of all the fundamental particles to me. I'm not quite sure why. It's partly that it's such a mysterious little object, and even today there are still lots of aspects of neutrinos that we don't really understand fully. The Standard Model is a minimal theory. That is to say, we take what data we have, we write down the simplest possible model that's consistent with it, and then we go out and test and see how well we've done. And so far it's worked very well. But just recently there have been some hints that perhaps we haven't quite got the story completely correct with the neutrinos. So today I want to talk about where we're at and what we're learning about neutrinos. Remember what these particles are. This is a particle which is fundamental. It's one of the leptons. It has no mass, no charge, and no color, no strong force. So the only force of nature that it can feel, really, is the electroweak, truly the weak force of nature. Not the electric part, just the weak part. And this massless business is part of the mystery of the neutrino. What does it mean for a particle to be massless? It's incredibly easy to produce it. The other particle that's massless that we're most familiar with is the photon. If you take a photon, it's a traveling electromagnetic energy bundle, but it has no rest mass. You can't take a photon and make it sit still. It's always running at the speed of light. A neutrino is quite different from a photon. It is not a force carrier. It is itself one of the fundamental constituents. And yet what we're saying is you can't take a neutrino and hold it still. If it's massless, relativity says it's always going to travel at the speed of light. Now, a deep question that you could ask is, why is it massless? Okay, that's a little bit of a funny question. In the Standard Model, don't we just collect the masses and write them down? We fill out tables by looking at the data. So the answer is it's massless because it appears in experiments to be massless. But sometimes in the Standard Model there is a reason. For example, there is a deep theoretical reason why the photon is massless, namely gauge symmetry. Gauge symmetry is a principle. It's a symmetry of the universe. It has to do with the nature of electricity and magnetism. And if gauge symmetry is correct, then the photon must be massless. It works out from the mathematics. It shouldn't necessarily be obvious to the casual viewer, but it is a definite consequence. And there is no such principle associated with the neutrino. There is no fundamental or deep mathematical reason why it needs to be massless. So we have just said that it is because so far there's no experimental evidence for a sluggishness, an inertia associated with the neutrino. Supposing that we made a very delicate little experiment and we measured the mass of the neutrino and it turned out not to be zero after all. Maybe it's 0.00001 in some unit system, a tiny but non-zero number. Would that break the Standard Model? The answer is definitely not. You could just scratch out the zero in the table and replace it with 0.0001. Actually, you'd have to do a little bit more than that. The Standard Model, as it's constructed, really makes the neutrino special. There are certain characteristics of the neutrino. For example, the fact that every neutrino in the universe, as it's running away from you, has a spin which points counterclockwise. It's a left-handed particle. That would also have to be modified. That statement about the world would get fixed up if we discovered that the neutrino has mass. People have been looking for many, many years, making very delicate measurements of the production and detection of neutrinos, trying to see if they have some mass. We have no direct evidence yet, so whatever it is, it's a very, very small number. But we do have some hints now that maybe it isn't zero. There's another aspect of neutrinos that's very important in our present understanding of them. There seem to be three different kinds. We call them flavors of neutrinos. It's just a kind of a whimsical name. There's the electron flavor, the muon flavor, and the tau flavor. And they seem to be distinct particles. In fact, now we talk about electron number as a property of particles. An electron or an electron neutrino both have electron number 1. So electron number apparently is a conserved quantum number in nature. As particles move and interact, an electron could just bounce, preserving electron number, or it might undergo a weak interaction So a little W boson might be exchanged and particles transform. The electron will transform, but only into an electron-type neutrino in order to conserve total electron number. Again, up until recently, it was believed that electron number and separately muon number and separately tau number were absolute, exact, conserved numbers. You know, Emmy Noether, a mathematician in the early 1900s, said that when you have a symmetry of nature, it's associated with a conservation law, and we don't have any symmetry of nature that we've discovered that would correspond to conserving electron number. So it's sort of an accidentally conserved thing, and when that happens in nature, you're sort of looking, okay, can we find an experiment where we see lepton number changing? So again, this is something that we're hunting for, and I'm going to tell you about the way that we hunt for these things shortly. Let me leave the world of neutrinos for a moment and tell you about the sun. It seems disconnected, but we'll see there's a very close connection. For many, many years, physicists have been, and astronomers have been trying to understand what the sun is and how it works. Very obviously very important thing for an astronomer to know what the sun is, because after all the other stars are suns as well, and this is the closest one. We can study it very easily. So people have constructed what you might call the standard model of the sun. I use the word standard now in completely the generic English sense. It's just a kind of an ordinary, everyday model of the sun that people can accept and believe, that describes how it behaves and how bright it is and the color and what it's made of and all the things that you associate with it. This truly is a model. It's not a fundamental theory of nature. We've just got a big ball of gas and we're trying to describe it as accurately as we can. And there are certain things about the sun that are very difficult to measure, like how hot it is in the middle. We can't get down there with a thermometer. So we have to make deductions based on what you see on the outside and based on the laws of physics and nuclear physics as we know them. What should the temperature be in the middle? So the standard model is a kind of a collection of all the branches of physics, heat and thermodynamics and light and sound and vibration and materials, all put together to describe this object. And it's a very successful model. It can predict all of the features of the sun down to details like sunspots and solar flares. To a certain extent, we have a good understanding of the sun. One of the aspects of that understanding is the nuclear reactions at the core which power it. We know how bright it is, so we know how many such nuclear reactions are occurring very, very precisely. And we know what they are. It involves protons smashing together with other protons at very, very high temperature and energy, forming nuclei. It's a strong interaction of nature that binds protons and neutrons together. Here you've got protons binding to protons, and in order to stabilize, one of the protons has to turn into a neutron, effectively. And that is a transformation that's a weak decay, and so a neutrino is released. And so according to the laws of nuclear physics, if you know how many nuclear reactions are going on, you know exactly how many neutrinos are coming out of the sun. So the standard solar model makes a very definite prediction for how many neutrinos flow out of the sun every second, and since we know how far away we are, how many are passing through us, our bodies, our detectors. A long time ago, in the 1960s, a physicist named Ray Davis decided, this number is a big number. It's, to be exact, I believe it's 60 billion neutrinos per square centimeter per second everywhere here at the orbit of planet Earth, almost 100 billion. That's a big number. So even though these neutrinos are very low energy, they're coming from low energy nuclear reactions in the sun, and even though neutrinos are very wimpy particles, if we built a big enough detector, thought Ray Davis, we should be able to find evidence that there really are these neutrinos coming from the sun. Right? After all, any individual neutrino has a tiny probability of interaction, but you've got an awful lot of them. So you're buying a lot of lottery tickets, and if you could build a big detector, you would just be increasing the number of nuclei available for those little neutrinos to bump into. So what are you going to do? Ray Davis looks at all the various nuclear reactions where neutrino comes in, hits a nucleus, makes a transformation occur, and his favorite was if you take a chlorine atom and a neutrino hits it, the neutrino will convert into an electron, because it's a weak interaction, and the chlorine nucleus will convert into an argon nucleus. That's what was known from nuclear physics. And argon is a gas. And it's not only a gas, but this argon that you produce is a radioactive gas, so it should be fairly easy to detect. A little Geiger counter would click if an argon atom was nearby and decayed. So what we need is a big tank filled with chlorine. What he used was cleaning fluid. Very clever, because it's carbon tetrachloride, so it's got lots of chlorine atoms in it, but it's also quite innocuous stuff, not a big biohazard. He took a railroad car, a tanker, and filled it up with carbon tetrachloride, and then he buried it deep in a mine. It's the Homestake mine in South Dakota. And why did he bury it in a mine? We're looking for a very, very tiny signal. Only once or twice a day is such an event likely to happen, according to the laws of particle physics, which he knew about in the 1960s when he built this device. Now, if you put this detector up here in this room, remember there's cosmic rays coming raining down on us all the time. And cosmic rays can also make nuclear reactions happen, and at a much higher rate, because the cosmic rays interact electrically as well as weakly, and strongly as well as weakly. So you would just be completely swamped out with other stuff going on if you did the experiment up here in the room. It's like if you're looking for a really dim light. You're not going to go into a bright room and look for the signal from a really dim light. You're going to go into the darkest room you can possibly find. So they went deep down into the Homestake mine in South Dakota, and he just started waiting. And the idea was, every now and again, a couple of events a day, a single atom. I mean, you got to realize the spectacular scale of this experiment. 1 or 2 atoms in this railroad car is going to transform from chlorine into argon. Argon is a gas, so it'll bubble up to the top. You have some collectors up at the top, and then you hold them in front of a Geiger counter for a while, and you see if a radioactive argon atom appears. He would sweep through the tank with some other gas to collect the individual argons, and it worked. It was an amazing experiment, and indeed, every month he would get, a couple of dozen atoms collected. Now, remember, Ray Davis knows what the prediction is for the total number of neutrinos, and he knows all the nuclear and particle physics of the day, which is pretty much the same as what we know today, almost. And so he could make a quantitative prediction. The standard solar model combined with the standard model of particle physics says you should get so many neutrino events per month. And what he got was about a third of that. Now, at first, people were just very proud of him. He did this great job. This is, in a certain sense, the first direct proof that neutrinos come from the sun. You might even argue it's the first direct proof that the sun is really undergoing nuclear reactions. Very cool, good stuff. But after a while, he kept running. This factor of 3 started to bug some people. Why are we seeing fewer neutrinos by a big factor coming from the sun than we predicted? At first, it was known in the literature, and it began to sort of grow and be called the solar neutrino puzzle. Where are the solar neutrinos? And, I think even when I was a graduate student, I remember reading about the solar neutrino puzzle, and most people said, come on, maybe he's like missing a couple. I mean, these are atoms in a giant tank. Maybe he doesn't collect them all. But he was a great physicist, actually is. He's still working on this experiment, and he did a lot of careful checks. For example, he would take a highly radioactive source and put it right next to his tank. Now he's got a source, and he knows how many neutrinos are coming out of it. And then he did collect what he expected. So there really did seem to be something special about the neutrinos from the sun. He really seemed to understand his tank. This kept going. He was collecting more and more data and improving the accuracy. And now, finally, other people began to get interested. There were several new experiments in the years after this, in the 80s. The United States got together with the Soviets, and we built something kind of like it down deep in a mine, but instead of using chlorine, we used gallium, which is a big tank of liquid metal, and the gallium would transform. The neutrino turns into an electron, and the gallium turns into germanium, and we can count and collect the germanium. And there was a European experiment also that was done with the same idea with gallium. Both of those independent experiments agreed that the number of neutrinos coming from the sun is fewer by a factor of 2 in their case, or 3 in the chlorine case, than what we expected. So the solar neutrino puzzle is just getting bigger. It's not going away. The Japanese entered the story with a giant water detector, a giant tank of very, very pure water. It was called Kamiokanda, deep in a mine in Japan. And again, it's a neutrino coming in, whacking into the water, making a transformation. And now this time, you have something extra. When the neutrino whacks into the nucleus or the electrons in the water tank, the transformation occurs, some energy is dumped, and that energy carries the momentum of the neutrino. If the neutrino comes in from a certain direction, you'll get a little spray of particles going out in that direction. So you line the tank with detectors, actually just light detectors. Big photomultiplier tubes is the name for a big light detector. And now you can actually see which direction the neutrino was coming from. And so, for the first time ever, not only do we have evidence that there are neutrinos, but now there's direct evidence that they really are coming from the sun. In fact, Kamiokanda and its second generation upgrade, Super Kamiokanda, which is even bigger, this is gigantic, okay, many, many stories tall. It's like a 10-story building filled with water. And they have produced images of the sun. Beautiful, beautiful image, because you're actually seeing, the neutrinos that are coming right from the center of the sun. And now, instead of seeing the sun in light, you're seeing the sun in neutrinos. So we're starting to do some astrophysics. But again, they see fewer neutrino events than they expected by about a factor of 2 or so. So everybody is agreeing that there is a solar neutrino puzzle. By the way, a little footnote, there was a tragic accident at the Super Kamiokanda facility just a year or so ago, as they were filling it back up again with water after a routine cleaning. One of the photomultiplier tubes imploded, and the shock wave traveled through the water and made a chain reaction, and they lost thousands of these photomultiplier tubes, millions of dollars of damage. And so this wonderful detector is now shut down. Hopefully it will get rebuilt, because it was a great facility doing all sorts of good neutrino physics. So how are we going to understand this puzzle? People, I think, by the time all of these experiments get put together and they're all agreeing with one another, you can no longer dismiss any one of them as just experimental uncertainty. There's two obvious places where we might be not understanding the world correctly. Maybe we don't understand the sun. Maybe the standard solar model is just wrong, and there are fewer neutrinos produced in the sun than we thought. There are various reasons why you would believe the standard solar model. It's a good, robust model, and of course, those folks were paying careful attention to these experiments. And as the years went by, they were refining their model, coming up with new tests. In recent years, they came up with a lovely test. If you understand the sun, including the detailed structure of temperature as a function of distance in the sun, you can predict the resulting vibrations of the surface of the sun. It's called helioseismography. It's like measuring seismic vibrations on planet Earth, but we're actually watching the sun vibrate. And the pattern of vibrations is very sensitively dependent on the solar model. If you change the temperature in the middle of the sun a little bit, you change the pattern of vibrations a lot. And it's working very, very well. So it really seems like we understand the sun. And we certainly know the total number of neutrinos because we know the total brightness of the sun. So I think the standard solar model folks defended themselves very well, and we sort of feel like we're almost obligated to believe what they're telling us. It's very robust data. So what else could be wrong? Could be particle physics. Okay, so here's the wild idea that people came up with actually fairly early on in this story. Supposing that what I said in the beginning of this lecture, what the minimal standard model says, is wrong. Supposing that an electron-flavored neutrino, which is produced in the nuclear reaction in the sun, is traveling the long travel path from sun to Earth, and as it's moving along, imagine if it could oscillate in flavor from an electron-type neutrino to a muon-type neutrino. Why would this happen? Turns out the laws of quantum mechanics say that if you have massive neutrinos, if they're not truly massless particles, then this can happen. It's one of those weird quantum things that's really hard to understand, but it comes out of the math. And in fact, we've seen exactly the same thing happen before with quarks. A down quark can oscillate in flavor, if you like, into a strange quark. We've observed this phenomena. It's a fascinating phenomena in the quark world. which we haven't had time to talk about. And it works in the quark world because the quarks have mass. So you need the neutrinos to be massive for this story to explain what's going on. And if they're massive, then it's allowed to happen. The rules of quantum mechanics allow an electron-flavored neutrino to turn spontaneously into a muon type. And in fact, it'll turn into a muon type or a tau type and then back again. It's a kind of a cyclic oscillation. So how am I visualizing this? You've got a bunch of neutrinos leaving the sun, and they're all electron types because that's what the nuclear reactions in the sun produce. It's a beta decay. Beta decays produce electrons and therefore electron neutrinos. Now they might oscillate on their way, and by the time they get to Earth, half of them might be electron-flavored and half might be muon-flavored. And every detector that I've described so far was specifically designed to look for the transformation where an electron-type neutrino produced an electron and some other transformation. If you had a muon-type neutrino coming in, it wouldn't do a darn thing in your detector because it doesn't have enough energy to produce the muon that it needs to produce. Muons are very, very heavy particles. So muon neutrinos would just go cruising right through your detector, and the electron neutrino, those are the ones that you would detect, and that might explain why you're seeing fewer than you expected because you're only measuring one flavor. Okay, it's like you go to the store and you buy a pint of vanilla ice cream, and as you're walking home, quantum mechanics takes over, and some of your vanilla ice cream transforms into chocolate and into strawberry. So by the time you get home, you've got this Neapolitan, I think it's Neapolitan, and if you only like vanilla ice cream, then you say, hey, I bought a pint, but now I've only got a third of a pint because I don't want to eat that chocolate and strawberry. It's a slightly weak analogy, but that's the basic idea here. If that's true, how could we find out? What experiment can you think of that would verify that there really are the total number of neutrinos coming out of the sun, but they're simply changing flavor? The Canadians came up with a great idea, and they built another one of these underground neutrino detectors. It's in a little town called Sudbury. It's the Sudbury Neutrino Observatory, and so it has the wonderful Canadian acronym SNOW. And SNOW is designed to make the following detection. First of all, it does the same thing as all the other detectors did. It can see transformations. It's a water detector. But they also have the possibility of measuring a weak neutral current. Remember that the weak force can manifest itself in two different ways, according to the standard model. The obvious way, the way that has been seen since the 1930s, is where a neutrino transforms into an electron, and at the same time transforms whatever it's hitting from one nucleus into another. That's the usual beta decay weak interaction. But Weinberg and company discovered a new force of nature. It's the weak neutral force, mediated by the exchange of Z bosons. It's neutral. There's no transformation. A neutrino just comes in, exchanges a little virtual Z boson, and whacks the nucleus. No transformation happening. Neutrino in, neutrino out. So what do you see in the laboratory? You see a nucleus just sitting there happily, and then all of a sudden, boom, it gets knocked into by something invisible. And so you can detect the presence of the neutrino by this weak interaction. And all you see is just a little recoiling nucleus, which will show up as a little light signal in your detector. So they built this thing capable of detecting. Now, this doesn't care what flavor neutrino you have. An electron neutrino can bump into you, a muon or a tau-type neutrino, it doesn't matter. They will bump equally strongly. It's a low probability event, so you have to be patient. And they've been running now for over a year, and indeed, they have begun to publish their results, and they're seeing the full solar neutrino flux when they look in this weak neutral sector. They're seeing them all. So the sun is, after all, behaving just as we thought. There is the full total number of neutrinos, and it really does look now like some of them are transforming into other types. Because when they only look at the electron type, they're seeing the usual reduction. But when they look at them all with this neutral current, they see everything. So that's big news. Okay, we seem to now have evidence that neutrinos can change flavor, and therefore, according to quantum mechanics, that neutrinos are massive. So now it's a big experimental effort. There are lots of new facilities being designed, coming online to try to pin the story down. I'm sure that in the near and distant future, you will be reading newspaper articles about neutrinos as we discover what kinds there are and what's the likelihood that one will transform into the other and what's their mass. It's fun stuff, and it's also pretty esoteric stuff. I mean, I know that a perfectly legitimate reaction to all this is to say, well, it's interesting, but do we really care? I mean, why does it matter if the neutrino has mass or doesn't have mass? So let me sort of finish up here with a discussion of a number of reasons why you might care, ranging from the kind of theoretical to the more applied. The most important theoretical reason that I can argue for why you care is we have this standard model of particle physics, a framework for understanding the world. It's been around for basically 30 plus years now, and it says the neutrino is massless, and once an electron neutrino, always an electron neutrino. This would be the first time in my professional career and in many physicists' lifetime nowadays that we would have a breaking of the standard model. And that's a pretty big deal. If you break the standard model, then it means that our understanding of the world is really not complete, and we expect that it's not complete. So that's exciting. It's a shift in our worldview. It's not a complete destruction of the standard model by any means. The whole picture still holds together. After all, in the quark sector, we had up and down quarks. They were both massive. And then in the lepton sector, we had the electron and the electron neutrino, and one of them was massive. Shoot, why isn't the other one massive? It almost seems like it should be. It seems desirable that the neutrinos should have mass. It's lovely and symmetrical. It would make the standard model nicer. It was a slight artifice of the physicists of the 1960s to say, well, the neutrino is massless. They were trying to keep the theory as simple as they possibly could do, and by making it simple, they had to make the neutrino this oddball, the massless particle. So now what we're suggesting is maybe the neutrino isn't such an oddball, it just happens to be quite light. And it took a while for us to figure that out. So there's this breaking of the standard model aspect that makes it interesting to physicists. Then there's the practical aspect. And it's not practical in the sense of, American consumers, at least not yet. I'm not talking about neutrino TV, but we are talking about an astrophysical use of neutrinos now that nobody had ever even dreamed of even 20 or 30 years ago. Right, we have now formed images of the core of the sun using neutrinos. That's a wonderful tool. It's a tool for other scientists. And now you can start to, think of all the possibilities. Not only could we measure the inside of the sun, there's no other way to get information directly from the inside of the sun. The only reason this works is neutrinos are formed in the middle of the sun, and then they have a tiny probability of interacting. Even though the sun is hot and dense, most of them just make it right to our detectors without hitting anything along the way. In fact, most of them go right through our detectors. That's why we need such big neutrino detectors. Light is produced in the center of the sun, and it immediately bounces around and gets absorbed by other atoms. It takes 1,000,000 years for light to reach from the center of the sun to the outside, and by then it's undergone so many interactions that we're not seeing the middle of the sun, we're seeing the edge of the sun. You could imagine looking at a supernova and the core of the supernova, something that's unimaginable by regular astronomy, or the center of our galaxy. So it's a tool, neutrino astrophysics, and this is now beginning. If you want to do neutrino astrophysics, though, you really better understand neutrinos. You can't do neutrino astrophysics and say, well, we're not sure if it has mass or if it oscillates, because you're going to be off in your predictions about the center of some galactic phenomenon by factors of 2 or 3, unless we figure out what the story is with the neutrinos. So this is a motivation for the particle physicists to get their story straight and figure out what's going on. The third consequence is kind of a very large-scale consequence, cosmological. Cosmology is the study of the universe as a whole. How did it begin, the Big Bang? How did it evolve to where it is today? And where is it headed in the future? It's the big question, in a certain sense. Where is the universe headed? Now, remember, the sun is producing these just gigantic numbers of neutrinos every second, and it always has been, and they're all flying out. Most of them just continue to fly along their merry way in straight line path essentially forever. And every star in the universe is doing that. So the universe is just filled with neutrinos. the number of neutrinos passing through us are these astronomically huge numbers, and there are neutrinos other than the ones coming from the sun. There's neutrinos coming all the way back from the very Big Bang itself. Now imagine for a moment that these neutrinos have mass. Okay, that's a new idea that we're just beginning to wrestle with. If all of those neutrinos have a tiny mass, you add up a whole lot of tiny numbers, you get a big number. You think about the effects on, say, a galaxy. If there's a whole bunch of massive neutrinos floating around, they're going to gravitationally attract. Right? Mass creates gravity. So as the universe is expanding, and we are observing that it's expanding, all these massive neutrinos are pulling it back again. So if they're massive enough, we don't know yet, but if they're massive enough, they may produce enough gravity to turn around that expansion, halt it, and then we might end up with a big crunch, the opposite of the Big Bang. So this is, the fate of the universe may rest in the hands of this exotic little wisp of a particle.